and it's great to be here. I like the Mood project a lot. It's a cool project. I'm going to talk about climate-sensitive infectious diseases particularly, and there's going to be a lot of talks in this session on climate-sensitive infectious diseases. As Anna Paula said, I'm leading a group now in Heidelberg University, about quite a large group, about 25 people or so. And we do data science and infectious diseases, and specifically some with climate sensitivity. It's not how we build the models, though, because we try to build the models from a multi-driver perspective, and I think that's very similar to what's actually has been the approach to the Mood project. Yeah, so I have a few things I would want to talk about. I wanted to start off with just introducing the area of climate-sensitive infectious diseases, and it might sound small, but it's actually a huge area. A paper published a couple of years back in Nature Climate Change documented more than 1,000 pathways are climate sensitive or have some documented climate sensitivity. That doesn't mean that it's the only thing affecting the disease, but it means that climate is involved in a lot of infectious diseases, more than 150 infectious diseases and more than 1,000 pathways. I'll talk more about vector-borne diseases. It's those that are a little bit more well-known and well-studied. So I'll make some examples, and I specifically give some examples of studies that have relevance for Europe. I just want to mention this first. And I think it's quite important, and especially maybe with the focus on emerging infectious diseases and the wider focus, although there is a lot of studies on vector-borne diseases and climate change, it's not the only ones that are affected. So there is much more potential pathways, and as you saw from the previous graphic, oh, something happened. I think it's thinking. Nice, thank you. Oh no. Okay, thank you. Yeah, so it's just most of the research effort today, I think, has been focused on vector-borne diseases, and maybe that's natural because it's a little bit more easy to link, and the linkages are likely less complex. But I think there's quite a few examples in the Mood project as well that documents pathways and linkages between other zoonotic diseases and climate change, and I think we'll see much more in the future. And that's really important because without studies documenting linkages, there's not much evidence for action, both in preparedness and pandemic prevention, but also in climate adaptation and climate mitigation. Okay, so the first angle in terms of climate-sensitive infectious disease that I wanted to take is looking at thermal biology. And thermal biology of insects, I think, is pretty cool because it's a direct linkage between models and experimental data. And you could use the models in order to actually make more meaning out of experimental data, in my view, at least, more meaning. In order to construct a suitability and R-naught estimates from experimental results or your suitability. And this is not a new field. Often the integration of the data and the parameters from the experimental data is used using a Ross-McDonald type of, vectorial capacity or basic reproduction number formulation. I'll give some examples of studies here. We've been working quite a lot on this, particularly for West Nile virus recently, and basically with the aim of trying to look at how trait dependence on temperature could be combined and could be combined across different mosquito species. and to capture the mosquito species virus interaction. And this has been done to some extent before, but there's uncertainties in the mathematical structural approach. There is also uncertainty that could be derived from the experimental combination of data into those traits, and it could easily be approved. So, in this paper, which is still under a preprint, we develop an approach, a Bayesian statistical approach to trait estimation, capturing experimental data variability and also borrowing strength from specific Culex species when estimating other dependencies and so on. So that's quite useful. Just to give you a little bit of a background to this type of estimations, what we are using in this study is a exotic cycle model framework which captured immature life stage of the mosquito, captures the adult life stage of the mosquito and the interactions with host birds. And this is likely how we see it, the most climate sensitive processes in the amplification and transmission cycle. Of course, there's also a human spillover effect, but it's thought to be less climate sensitive. So this was what we wanted to focus on in this study. Most of it, though, is, or all of it is, though, is focused on the mosquito sensitivity and less on the host sensitivity when it comes to the bird. So there could be obvious, and there's likely to be obvious sensitivities in terms of bird migration patterns and changes in bird migration and so on, but that's not well understood at the moment. Just to give you an idea of how this actually comes together, here's some traits of mosquito species shown, PPNs, restaurants, for example. In the different colors, you see different experimental data from different studies. You can see here that the traits for PPNs has more data, and other traits has less data. Combining this in one model framework, though, you could make use of, take advantage of a multi-species model for estimating these traits. There's quite a few traits that has some documented climate sensitivity, and those are listed here. It comes into in the lifespan, biting rate, hatching, etc. So there's a lot of sensitivities that has been documented, that has been experimented on, and where there is actually data points on the specific sensitivity. And when you put that together into a basic reproduction number formulation from Ross-McDonald framework, you could see how the R0 value, or the relative R0 value, transmission suitability, peaks around 23 to 26 degrees. That depends a little bit on the model structure. So we've actually modified the model structure and are more comfortable with the estimate we call main here at the top, which is a peak of 24.5 degrees. But all of the other estimates are also representing model structures from the published literature. So there is some structural uncertainty in the estimate of the optimal temperature range. Of course, now you could use these two real situations to look at potential, expected trends, etc. Although now comes a disadvantage with the experimental data. There's actually experimental data, and it's not observed. There's no competition. There is no drivers into this data. So that's obviously a disadvantage of this type of approaches, although it gives us probably quite a good understanding of the biological thermal optimum and limits of the vectors and the vector when it comes to transmitting pathogens. Other approaches that has been applied to study sensitivity and drivers of infectious diseases, again on West Nile. I'll give here by showing an example of a study looking at the outbreaks of West Nile across Europe using the TESI data from the ECDC reported into the European surveillance, and trying to predict the 2018 outbreaks, but specifically out of the books, out of the training data. For doing so, used annual data with bioclimatic, with some vector data, with some bird data, with some environmental data, satellite data, etc., and socioeconomic data at the nuts tree level. So this is a rather cruder geographical resolution, although the advantage is that it actually uses a wider scale, which means that climate can actually vary in this geographical region quite a bit, not only due to altitude shifts, but also due to spatial ranges. Combining predictors, which were quite a few, into different categories, climate and bioclimatic variables comes out as an important predictor in this study, together with the water index from satellite data, demographic variables, vegetation index, socioeconomic, while vectors and host is coming out lower. Doesn't mean that they're necessarily less important, actually, but these data of vectors and hosts is also probably competing with the other drivers, and they're also admittedly of lower quality at this geographical and temporal scale. Anyway, if we choose to believe in that this model has some predictive ability, which it actually indicated to have on the 2018 outbreak, where it actually predicted out of bag the so far largest outbreak reasonably well. We could use this model, this predictive model, to look at, for example, how trends are changing in terms of suitability and outbreak risk of West Nile, which is predicted in the graphic to the right here. It's just changing over time trends of the outbreak risk of West Nile in Europe. And as you might see, it's actually extending beyond data into historic time. So we can't actually validate that period. And there might have been some cases, who knows, but maybe not at all. What we also could do with this model is to experiment into future scenarios, what could actually happen in the future. So for West Nile, it looks like, according to this model, that if the climate would change according to climate scenarios, we could have a quite dramatic shift in the distribution of the transmission. This doesn't incorporate other drivers, though, because the other drivers doesn't actually come in a nice format for good reasons. It's difficult to project in the climate scenario. So we don't have, for example, bird behavior, bird migration patterns, or socioeconomic development in this projection. So it should be taken as a experimental projection, but it could still be quite kind of informative in the sense of, maybe this is, if this model and these predictions work out well, this could be a potential development in the future that we need to consider in our preparedness and surveillance and also climate adaptation efforts. So that's one take home. Scenarios can be used for adaptive efforts, of course. One could also do predictions at a finer scale, maybe to target surveillance and control efforts in a more timely fashion, but that would be different usage. So different adaptation strategies would be connected to such scenarios. So another scenario exercise that I wanted to show, and I think it's a little bit interesting because it contrasts quite a bit from the other one on West Nile. So West Nile in Europe, according to that model, was huge changes in the geographical outbreak risk areas predicted. And here is another projection and model. It's built around Swedish data on tick-borne encephalitis. And tick-borne encephalitis, it's at a very fine granular level. Originally, individual data that was aggregated to finer sort of municipal level, much smaller and finer than the nuts tree level. And then we used a spatio-temporal framework in Bayesian INLA framework to predict the spatio-temporal patterns at the fine scale and at the annual level of the tick-borne encephalitis epidemiological cases in across Sweden. The predictors that came out was NDVI as really important, temperature, minimum temperature of the third quarter, 1 month lagged. Also roe deer population density and population precipitation was actually negatively associated with risk predictions and incidents particularly. This model works reasonably well. It's not a perfect, as you can see in the validation of the testing data here. It's not a perfect correlation, but you see some resemblance with the predicted cases and incidents and actual incidents. So it captures some of the patterns. If we would plug this into, again, a climate scenario, which could be quite reasonable, because one of the decisions that you might want to do in terms of TB is actually vaccine deployment, vaccine coverage, and vaccine strategies. Here, the graphic to the right shows an going trend in predicted according to a regional climate model scenario for tick-borne encephalitis in Sweden, and the graphics and maps to the right show how this expansion is projected in those scenarios. So the bottom is a high emission future, so it's quite a dramatic warming, and the top is current situation. So you can see some changes in the geographical patterns, and you can also see quite a bit of changes in the incidence as well predicted. This would assume vaccination, roe deer, etc., would be according to today. So it's more or less a counterfactual today with a different climate that we show here. It's not so much the future, it's because we don't have the other drivers of vaccination. I assume would likely change, and perhaps even because we're able to do this type of predictions and projections, we inform the vaccination to change. So there's like a iterative loop. How much time do I have left? 2 minutes?
Yes, 5 minutes.
Okay, cool. I also wanted to mention, so I've talked a lot about models and large-scale models. I wanted to mention some other aspects of work that we're doing in a project that I'm leading called ID Alert, which I think has a little bit of similarities with Mood, but more into specifically climate, investigating the climate sensitivities and putting forward strategies to deal with it and tools to deal with it. One of the challenges is obviously data, and really to bridge the data gap would be one of the more important issues in the future. Another challenge is the transformations of societies, including nature-based solutions, restoration, urban parks, wetlands, etc., which is both addressing a lot of the global goals, but at the same time maybe causing suitable breeding sites for mosquitoes, and amplification of potential amplification of some pathogens. Yeah, so in this project we actually do study these issues, both the transformation process, but also the impacts, hazards, preparedness components linked to climate, early warning systems, longer-term projections. The main bulk of the research is though on vector-borne diseases, so there is quite a lot of mosquitoes and ticks, but there is also a little bit on other zoonotic diseases. One of the study areas is Barcelona, and here we figured out together with the public health agency that if we change this, if they wanted to change the storm drains in Barcelona, and we figured out in the project development phase that yeah, maybe we should change them in a way that we could really evaluate the consequence of changing the drains. And Marina, who's here in the back, she's leading a trial in the project for the evaluation of the storm drain intervention, which is randomized. So it's basically randomizing how the drains were changed in the city. And the drains are changed in the way that they can't accumulate water after rain, which the public health authority had observed associated with mosquito breeding and mosquito abundance. We'll have a result. When will we have results on this, Marina? Maybe in half a year or something. Yeah, but it looks very promising, the intervention. There's also other aspects of, so that is like adaptation or preparedness in a sense, in an infrastructure sense. There's also a lot of efforts on novel data streams in the project. So one is the mosquito alert activity, which is a citizen science activity to get more mosquito reports. And this has actually led to the detection of the emergence or the abundance of mosquitoes in new places in Spain, for example. And in a similar way, we develop a tick citizen science data stream starting in Sweden, where there has been tick citizen science, people sending images of ticks for some years. In the beginning, that ended up in an email inbox somewhere. But now we're actually automatized the process of analyzing those images and classifying the specific tick species by image recognition in the project in order to be able to detect the emergence of invasive species, for example, and particularly Hyaloma has been one of the tick species that's been high on the agenda to detect that emergence. There's also a bioacoustic stream, which is quite interesting, and that's actually using just acoustics in order to do recognition of bird species and potentially even later on of other animal species. And there's also a smart mosquito trap surveillance stream, which is tested out in those case study regions. So we are testing different data streams in order to be able to do better predictive models, for example, to have better data, to be able to talk about the consequences of these transformations like nature-based solutions, and in order just to have a better understanding of the development of the situations. That was all I wanted to say. Now, see if there's any questions.